Hi, welcome back. A couple of people asked me for the slides. The slides are actually available on a H2O exercise GitHub repository. Actually, let me bring back the slide for that. So if you git clone this, then you'll get the 3 PDFs for the 3 presentations. All right. So for the second part of the talk, I'm going to present two components that we'll be using afterwards in order to tinker a little bit, I would say, with HTTP2, like to get an actual experience with a couple of tools. And so I'm going to talk a little bit about H2O first. Which is the web server that we've been using that's open source. The address on GitHub is h2o/h2o. There's another H2O, which is an artificial intelligence project, so we get bug reports that I don't understand from time to time. So it's a fairly open license. It's an MIT license, and it's been developed since 2014, and we have been using into production since mid 2016. And I think I've mentioned that, but like around 25% of our traffic is HTTP2. So in terms of features, it's actually it packs a lot of features in a relatively small code base. It already supports TLS 1.3. It's multi-threaded in a way that the way you typically use that is that you have one thread per core, and then every single thread is event-driven. So you have an equal loop for every single core. It also supports libuv, but that's more for development purposes, so that you can build it on a Mac. So if you're developing on a Mac, that works as well. It supports all the SSL libraries out there, Libre, boring, and open. It also has like an embedded Ruby that you can execute on the fly. So if you want to tweak responses at this level, you can. There's actually a huge amount of work going on there in order to be able to request Redis to use as a cache, etc. So if you're interested on that side, I would encourage to take a look at that. It's actually composed of many different libraries, which are usable independently. There's a Pico HTTP parser, which I know some Python libraries use. It's a super fast HTTP parser that uses SSE instructions to do the header parsing. Somebody from Intel actually contributed AVX instructions parsing, which is even faster that we haven't merged yet. There's Pico TLS, which is an implementation from scratch of TLS 1.3 that's been used for the quick implementation that we will merge into H2O when the quick draft is done. There's Never Bleed, which I mentioned earlier following a question, which is a response to the Heartbleed issue that OpenSSL had, where you would send private keys in response to malformed packets. So this makes the SSL part of things and the traffic part of things separate, and you have a separate process that knows about the keys, and then the traffic process that calls into that process to do the handshake. And then there's a server started, which is a pretty cool feature, makes use of the go away frames, so it's integrated with H2O, and that allows you to restart a server without the browsers noticing anything. They will just reopen seamlessly new connections and reconnect to the new instance of the server. And you will keep the old instance of the server as long as there are browsers connected to it. It has an extensive test suite, both in C for unit tests and Perl for end-to-end tests. So we use curl and ng-http to send requests, and then a pluckup, which is a Perl server on the server side to do all sorts of tests for headers, etc. So we have all the tests are run in Travis for every CI. We have integrated Coverity. I don't mention that in the slides. And we also run the builds under ASAN. And we actually applied to Google open source fuzz project. So if you don't know about it, I strongly encourage you to take a look at it. It's oss-fuzz.com. And Google essentially takes your open source project and runs the fuzzer continually on their systems. And the deal is that if they find a crash, then you have 90 days to fix the crash. Otherwise, they will make the crash public, which I think is a pretty good deal. And so what we have a fuzzer for the URL parsing, and we have fuzzers for HTTP1 and HTTP2 reverse proxy and request handlers. So yeah, and those run continually on Google servers. It uses a YAML format config file. So this is like the default config file where we open 2 ports and then have one HTTP, clear text HTTP connection and the TLS connection with 2 different host names. In terms of performance, so it's super well integrated for pushes. It knows about Casper, so because most of it because Kazuo, the main author, came up with the idea, and so that's implemented in H2O. It does MIME-aware prioritization, which I was talking about, which means that if by there is a small window of time where the browser hasn't had the chance to reprioritize the streams. And so by default, H2O will do prioritization based on the MIME type, so that it's going to send the CSS and JavaScript before the images. The scheduler is O1, which makes it super performance. I never see it in the performance traces. It does TCP responsiveness, which is the bit I was talking about, where it estimates the RTT between the client and the server, and tries not to fill the TCP buffers to give a chance to the browser to reprioritize streams so that you don't have several megabytes worth of data by the time you get a reset stream out. So those are like cooked numbers. I think my main point with this slide was to show how well it scales. So the first test is doing using a single connection and running a bunch of requests. And so you can see that it does 700,000 connections a second. 70. I actually don't remember. Sorry. Oh, right. No, so the total is 771,000 requests. But for request a second is 77,000 on the core. But then as you add more connections, so on the second one, it's 6 connections. And you can see that we've scaled from 77,000 to 500,000. So it scales almost linearly with the amount of cores that you want to give to H2O. And the numbers themselves are pretty good. This is a benchmark on the web somewhere. I forget the exact address. But this is actually pretty cool. People write small examples using their libraries, and it compares them automatically. And so this is to give you an idea of where it stands. At the very bottom, we have Node.js, and there are even slower frameworks, obviously, because Node.js is actually pretty good in terms of performance. And you can see above H2O where it compares to the other fast HTTP implementations. One of the reasons it's super fast is the memory allocation usage. So it uses a memory pool. Every allocation that's done for the request is done to the pool, and when the request is done, we free everything in one go. It tries to use zero copy as much as possible. And then it has also like a thread level cache for memory. So if you glibc, for example, on Linux is pretty bad with memory fragmentation and doesn't work well if you have many threads. So a common workaround is to use jmalloc. The actual code inside H2O is fast enough that we haven't seen any difference between when switching from glibc to jmalloc. So I think that's a testament to the implementation there. We're still using jmalloc because jmalloc gives us statistics about the memory usage. So we're embedding this. It's actually in the open source version. It's organized in modules, so there are like 3 main components in H2O. The first one is the handler. The handler produces data that is sent to the client, and so there's a file handler that looks for files on disks and sends them to the client. There's the mruby handler that executes some Ruby code and then gets the response out of that. Then there are the filters that run after the handler has run and where you can compress stuff on the fly. So H2O supports Brotli and gzip. And then there's the logger where you can do stuff per request. I know a contributor to H2O has written like a Kafka logger, for example, based on this, so that you can send all the request statistics to a main site. The protocols themselves, they're all fairly straightforward implemented. If you go under a lib HTTP1, you have all the HTTP1 connection. The parser, obviously, as I've said, is a different project. It's PKO HTTP parser, but that's all embedded under the H2O umbrella. And then the HTTP2 parts are found under lib HTTP2. In particular, the main dispatch point for the connection is under lib HTTP2 connection. And if you look at handle something frame, then you will see all the callbacks that are called when we receive frames for a given type. So there's one for ping, there's one for headers, etc. So in this directory here, if you clone it, there's a hello world handler that actually uses lib H2O as the server, and the server itself just implements the configuration, timeouts, etc., and then the request handler. So I think that's it for the H2O side. Oh, sorry. Let me talk about the main data structures. So H2O context is the main context for a given thread. So the way it works is that when a request arrives on a given thread, it never leaves the thread. And that's true even for reverse proxies. So both the client side and the server side connection are all going to live into the same thread. So that's how we avoided a lot of locking. There's no much inter-thread communication. Only for stats, that's the main mechanism we get data shared between threads. Then H2O socket is the low-level asynchronous API for writing to the network. And then H2OCon is a superclass that uses that abstracts the details between HTTP1 and HTTP2. H2O, the code base, does a lot of, and I detail that in the contributing.md file. It uses a lot of this mechanism where we have a superstructure to abstract the details of specialized classes. So in the exercise, there's a couple of things you can play with, and we'll see that detailed in the README. But the idea is that if you're interested into hacking H2O, those are a couple of ideas that you could play with. So have H2O serve different contents and see how the browser reacts, and how you can set up Casper, and how you can push with mruby. Let me talk a little bit about H2Get. So H2Get is a very simple H2 client that I wrote. The goal was that in our test suite, we were using curl and ng-HTTP, but if you wanted to write something that's not RFC compliant, then it was not possible to do. So I wrote this tool so that you could actually script how you would send wires on the wire. Sorry, frames on the wire. And it's the result. It's a very small C client. It's a couple of files. And it uses mruby as a glue. So we use the Ruby parser. And so mruby is, I don't know if you are familiar with that. mruby is a project sponsored by the Japanese government, the MITI, I think it's called. The big industry ministry, and that's spearheaded by Mats, the original Ruby author. And the goal of mruby is to be able to embed Ruby into small devices. So it's the embedded version of the language. So essentially in H2GET, we create an H2 object for each connection. And then we send something. If you look in the repository, there's all the list of the implemented functions to send frames. And then you use the read function in order to read frames from the wire. And then that creates a frame object, and you can output the type and the contents, etc. So there are like 4 files of interest. The main entry point, h2get.c, that does the connection establishment, and there's all the code that writes the frames into the wire. There's the h2get_read.c, where you read the frame and build the frame object. Then there's the mruby glue into a separate file. And finally, there's the hback.c implementation. It's a very crude implementation that I did. It only supports compression from the server because you have no way of actually opting out of it. But it doesn't do any compression when sending to the server. So when we send a status code, for example, or a request, we do actually write on the wire method get. And the other data point is that 80% of my implementation time was actually spent on writing the HBAC implementation, and all the rest was the H2 part. So that was a bit tricky to get right. Again, in the exercises, if you're interested in that part, there is one exercise to implement the decoding of integers as specified in the RFC. The RFC has pseudocode, and so I've created a branch that you can check out where this function is missing. And there are unit tests that accompany the function so that you can check that your implementation works correctly. And I guess that's one entry point into the huge HBAC RFC. So this is how you open a connection. So you connect to the server. So this does all the ALPN negotiation, right? And it does the SSL part of the connection. Then you send the prefix, which is the magic string that says, hey, I talk HTTP2. And then we use putS to read from the wire. Here, 1,000 means 1,000 milliseconds. So we wait up to 1 second, and then we shut down the connection. So this code would essentially connect to the server, send the prefix, and then wait to whatever, and print whatever the server is sending. This is a slightly more evolved example. There are full-fledged examples in the h2get repository, so you don't have to rewrite this from scratch. But here, I wanted to detail how actually you would establish the connection with the server. So you send the prefix, and then you send the settings. It takes a series of arrays. So here, number 2, you would have to look into the RFC. Number 2 means enable push, and 0 means actually disable. So here, the only setting we're sending to the server is that we don't want pushes. And then we have a loop that reads packets from the wire. And when the packet is a setting packet, if it's an hack, we don't do anything because it's hacking our settings frame. But if there's no flag no flag set for the settings frame, then we will send an hack for the server settings frame. So this gives you an idea of how, on the client side, you would implement connection establishment for HTTP2. Once the connection is established, then you can send requests, and this is how slightly evolved. You don't have to send priorities or anything, but this example does go through that. And so you first create the priorities. Here, it's not exclusive, and the parent stream is going to be 0. And then the weights are 16 on one hand and 32 on the other hand. And then we build key values for the headers. and then use the send headers function to actually send the headers to the server. We set the end stream flag in order to inform the header that there are no more headers to come. Sorry. Yeah, actually, I'm not sure that's right there. Huh. Never mind. But I guess yeah, sorry about that. I'm not entirely sure the send continuation there is correct. And then, but the idea is that you use the send headers, and that this constructs a headers frame that's sent over the wire using the priority indicated in the function itself. And that's about it. I would now encourage you to switch to the H2O exercise repository. There's a readme.md file, and there are like 3 tracks. And I would encourage you to do whatever interests you the most. And I would then go through the tables and try to answer all the questions that you guys might have as thoroughly as possible. But the 3 tracks are as follows. The first one is if you're not interested in coding, but you would like to see how you can observe the HTTP2 connection. It shows you a couple of examples of how to look for pushes in Chrome, how to use Wireshark with Firefox. So Chrome has net internals that you can use in order to view the individual frames, and I would say that this is like the easier thing to set up because there are no need for external tools. But then we go through an example of looking at the decoded TLS trace with Wireshark, which might be handy if you're decoding something that only happens with Wireshark. And I think that's it. Oh, no, so yeah, I think that's it in terms of observation itself. Then let me actually call the page. Right, no, so that was it. So Chrome and Firefox. Then there's the low-level clam track. I would encourage you to clone and build H2Get, try to establish a connection, see what different settings the servers are sending, because they're all different implementations here at Facebook or Google or Fastly, and you will get different settings and see how different they are. Try to get a go-away frame from the server. The RFC has a bunch of places where it says that doing X violates the spec. So, for example, one very easy way to get a go-away frame is that the send push setting in the settings frame only accepts 0 or 1. So if you're sending 2, you should get a go-away frame specifying the error. The reason I mention this is that it's actually very difficult to troubleshoot go-away on the browser because the error doesn't surface up in the browser yet. Maybe the GUIs will evolve, but actually the low-level frame always contains a string that details what really happened. And then another way would be to look at the ping frames. So try to ping the server, and Google does something different than the other servers do. So I would encourage you to take a look at how that differs. The HBAC thing, which I was mentioning, there's a branch that doesn't have the encoding done. And here's a link to the RFC. The RFC contains pseudocode, and it explains how to encode integers in HBAC. And then, yeah, I would encourage you to take a look at how that's done. And then there's a unit test that you can run to know if you're on the right track or not. And then finally, if you're interested on the server side, there are 2 exercises that I would recommend you do. The first one is that in the repository, there is a patch that you can apply to H2O that will make H2O dump the information of priorities. So you can see on the server side what we're receiving from the browsers. And so, for example, you could do that in order to play with Safari. I see that many people have Macs. And so to see which type of weights it gives to to the different requests. And there's also a www repository already with different JavaScript and CSS setup if you don't have anything handy. And then the second part would be, and if you are curious about to see how the different browsers send window updates, you could also look at the function that handles frames for window updates and dump that information. Finally, there's a makefile and a server.c into this repository that you can that's intended to use with H2O. So the makefile supposes that you've already compiled and make installed in H2O on your laptop. And then the server.c would link to that library, and then you can customize this server.c and see how you would write handlers in H2O. And I think that's it. That's the end of me talking. So I'll be available for questions.